Ella, would you mind putting down that book long enough to answer me a question?
Why, of course, dear. What is it? Oh, you're working on our budget again.
Well, we might as well call it your budget. It's your fault I can never make it come out right.
Well, you're the man of the family. That's your job.
But how can I see if we're getting along all right if you don't help a little? Just look at that checkbook.
What's the matter?
Have you bothered to look at the stubs?
Mm-hmm.
Look at this. $10. Well, what was it for? And this one's the same. But this is the prize. $25, and it says beans, bread, and tooth powder. $25.
I know what that was. I was going shopping, and that was the only paper handy, so I wrote them down there so I wouldn't forget them.
Well, that's dandy. Well, let's try and get a little order out of this chaos. What was this $10 for?
Oh, I don't remember. Doesn't make any difference, does it? You can make it balance, can't you?
I'm not balancing the checkbook right now. I'm checking our budget. Was it a house expense or for the dentist or personal spending money?
There you go again. Always splitting hairs.
That lady evidently considers splitting hairs a very small business. I wonder what she'd think if she knew that we're about to consider the splitting of something even more infinitesimal, the uranium nucleus. On the other hand, judging from what we've just overheard, maybe she'd prefer to keeping accounts. At any rate, as I've said, this excursion in science is to be devoted to the field of atomics, about which we've heard so much lately. And here's our science reporter, Emerson Markham, ready to clear up for us this matter of splitting the uranium nucleus.
Thank you, Bob Stone, and how do you do, everyone? We owe a vote of thanks to Dr. Kenneth H. Kingdon of the General Electric Research Laboratory, one of the pioneers in the field, who isolated U-235 back in 1940.
Our thanks, then, to Dr. Kingdon. Where does our story start, Emerson?
Before that, back in 1934 at the University of Rome, Bob. It was there that Professor Fermi and his colleagues were industriously bombarding most of the elements in the periodic table with the then recently discovered neutron projectiles. They found many cases in which the neutron was captured by the bombarded nucleus. The new compounded nucleus was unstable and emitted an electron to reach a stable form. This emission of a negative electron is equivalent to raising the positive charge of the nucleus by 1 unit, and thus changes the bombarded nucleus into a new nucleus appropriate to the next higher element in the periodic table.
Did Professor Fermi try bombarding uranium, Emerson?
Yes, and we can imagine that it was with very special interest that Fermi set about bombarding uranium, the last element in the periodic table, element number 92. Would uranium behave like so many other elements and, by neutron capture and electron emission, transform itself into a new element, number 93, which ordinarily does not exist?
Yes, I can see he might be excited. A new element. What happened?
Well, that seemed to be the case. Definite chemical indications were obtained of the presence of one or more new elements beyond uranium, the so-called transuranic elements. But the discovery gradually became embarrassing, for it was found that the new element was accompanied by many other elements which could hardly be accompanied or rather accommodated within the restricted spaces of the periodic table close to uranium.
Did he come up with a solution?
The difficulty remained for several years, Bob. 2 or 3 investigators almost stumbled on the answer, but it was not until January of 1939 that Hahn and Strassmann, by careful chemical work, demonstrated that most of the elements produced by neutron bombardment of uranium did not lie beyond or near uranium, but instead lay in the center of the periodic table, close to barium.
Explain, please.
Well, when a uranium atom captures a neutron, it does not always emit a light particle like a proton or an electron, but may split into 2 parts of nearly equal mass, thus producing much lighter elements like barium and krypton. News of Hahn and Strassmann's discovery was passed around by word of mouth and telegram, and experimental proofs of its implications were supplied within a few days, almost simultaneously, in Copenhagen, Paris, New York, Baltimore, Washington, and Berkeley. Frisch and Meitner, 2 scientists in Denmark, christened the phenomenon fission. The fission particles were detected by the very high energy with which they flew apart and so produced dense tracks in a cloud chamber, or very intense ionization in an ionization chamber.
Oh, by the way, Emerson, what causes this fission?
Well, let's look for a moment into the structure of the nucleus. The nucleus of the uranium-235 atom, that is important in this connection, contains 92 protons and 143 neutrons, packed into a sphere which is about a millionth of an inch in diameter. These particles are all in rapid motion. The protons carry positive charges, which of course repel one another, so that on this score, the nucleus should fly apart.
But I take it doesn't. Why?
This electrostatic repulsion is overbalanced by a special nuclear force of attraction, which acts between the nuclear particles when they are close together and makes the whole nucleus stable. The particles at the surface of the nucleus are acted on by this attractive force only from the inside of the nucleus, so that they are in much the same special situation as are the molecules on the surface of a drop of water.
How do you mean?
Well, in the case of the water drop, we know that this produces a sort of skin around the drop, which is characterized as surface tension, and which pulls the drop into a spherical form. An analogous state of affairs exists in the nucleus, and we may think of the attractive nuclear forces as producing a sort of surface tension around the nucleus which holds it together against the electrostatic repulsion of the protons. There is then a state of equilibrium between these two forces. But if the energy of the nuclear particles is increased sufficiently, the nucleus will become unstable against small distortions of form and will break up. For each nucleus, there is a characteristic value of this energy increment for which breakup or fission will occur.
And what brings about the fission, that bombardment you spoke of a while back?
When a bombarding neutron enters the nucleus, Bob, it gives extra kinetic energy to all the particles in the closely packed nucleus. This energy comes from two sources. First, from the kinetic energy of the bombarding neutron, and second, from the small loss of mass which the neutron experiences on entering the nucleus, and which is converted into energy, the so-called binding energy. For each nucleus, there is a characteristic binding energy for a slow neutron, and if this binding energy exceeds the fission energy, the nucleus will undergo fission by slow neutrons. For other nuclei, the binding energy will be insufficient to cause fission, but by bombarding with a fast neutron, the added kinetic energy plus the binding energy will be sufficient to cause fission. Now, these quantities can all be calculated, and it is found, in agreement with experiment, that U-234 and U-235 should undergo fission by slow neutrons, whereas U-238 and thorium-232 require fast neutrons for fission.
How did they ever find that out?
Definite experimental proof that fission of uranium by slow neutrons was due to the 235 isotope rather than the 238 was obtained in March of 1940 by separating very small quantities of these isotopes with mass spectrometers, both at the University of Minnesota and in the General Electric Research Laboratory, and then subjecting the separated samples to bombardment with slow neutrons from the cyclotron at Columbia University. The fission of U-235 is the basis for one form of the atomic bomb, and we shall consider the characteristics of the fission process which make it suitable for this and other applications.
Well, fine. Let's start considering.
Ingenious experiments, which we really haven't time to describe, have shown that fission occurs in less than a millionth of a second after the bombarding particle has struck the nucleus. This rapid action is, of course, necessary for the use of the process in a bomb, just as rapid combustion is necessary for an ordinary explosive.
Does the bombarded nucleus split into two equal parts, Emerson?
Oh, no, Bob, no. Nor does it always split into exactly the same pieces. It can be shown that the split occurs somewhat more easily, in fact, if the fragments have masses of approximately 140 and 90 units. The fragments fly apart with tremendous kinetic energy, the lighter fragment having somewhat the greater energy in order to satisfy conservation of momentum at the breakup. It is this high velocity of the fission fragments which furnished most of the heat energy for an explosion or for a source of power.
And just about how much energy would that be?
The energy liberated in the process, if all the atoms in a pound of U-235 could be made to undergo fission, would be 11 million kilowatt hours. This liberation of energy occurs because the fission fragments, as a result of their different nuclear binding, weigh about 1/1000th pound less than the original pound of U-235. And this loss of mass appears as a gain of kinetic energy according to the law of the equivalence of mass and energy. The energy equivalent to the 999 1,000th pound mass of the fission fragments is at present entirely inaccessible to us. Now, the fission fragments contain the same number of protons as do the nuclei of stable elements near the center of the periodic table. But the fragments have so many neutrons that they are unstable. They therefore settle down to a stable state, partly by emitting neutrons, but more often by emitting electrons, a process which is equivalent to the conversion of neutrons to protons, so that the emission of a single negative electron is effectively the same as having the nucleus lose a neutron and gain a proton. The fission fragments are therefore strong radioactive emitters of electrons and X-rays. This means that the fission products will find uses as X-rays, sources for therapy and radiography, and as radioactive tracers in chemistry, biology, and metallurgy. In conclusion, we'll note that from 1 to 3 excess neutrons are released when fission occurs. Now, at a later meeting, we're going to learn how these neutrons have been used to obtain energy from the nucleus in a practical way.
Thank you, Emerson, for a most interesting excursion. And ladies and gentlemen, if you would like to have a copy of a paper by Dr. Kenneth H. Kingdon of the General Electric Research Laboratory, which contains the facts we've just brought you, all you have to do to get your copy is address your request to Excursions in Science in care of the station to which you are now listening, asking for scientific paper number 225, entitled Splitting the Uranium Nucleus. That's Splitting the Uranium Nucleus, scientific paper number 225. Your copy will be put in the mail for you free of charge. And now, once again, it's time for our questions and answers. The questions which you're about to hear, ladies and gentlemen, have been sent in by people like ourselves, laymen with an active scientific curiosity. The answers are based on facts provided by staff members of the General Electric Research Laboratory or of other equally trustworthy institutions. All set, Emerson? Here's the first one. It comes from one of our friends who writes, "We are troubled with moisture collecting on some of the walls of our home. There isn't a furnace on because we can heat the house with one of those little oil stoves. Can you help us out?"
Well, in the first place, the moisture comes from the inside, not from the outside, and probably from the oil stove.
From the oil stove?
Yes. Very few people realize that every time you burn a gallon of oil, you produce considerably more than a gallon of water. This water comes off in the form of vapor along with other gases from the flame. Now, if our friend's stove is connected with the chimney, but if for some reason the vapor doesn't go up the chimney, it's going to get out into the room. Probably when the furnace is turned on and the small oil stove is no longer in use, the problem will automatically take care of itself.
A listener in Pittsburgh writes, "The following is quoted from a magazine article I read recently. Hertz's tremendous discovery, however, showed that visible light was just a special wavelength region of an infinite spectrum of radio waves, and that these waves all originated from motions of electrical charges." Now, what I'd like to know is whether daylight and sunlight are just a special wavelength from electrical charges. In fact, any visible light, candlelight, gas illumination, etc.
Well, yes, Bob, but daylight, sunlight, candlelight, gas illumination, and so on all have the same origin. They all originate in the vibration of electrons of the atom.
Well, next we have this inquiry from a lady who writes, "I have 2 kinds of baking powder on my pantry shelf. One contains cream of tartar, tartaric acid, bicarbonate of soda, and starch. The other contains calcium acid phosphate, sodium aluminum sulfate, cornstarch, and sodium bicarbonate. Which of these ingredients, if any, is harmful, and to what extent?"
Oh, none of these ingredients is harmful, Bob. The Pure Food and Drug Act and other supervision by the government sees to it that harmful food and food ingredients cannot be sold.
Now, next, let's consider this letter from a gentleman in Overland, Missouri, who asks, "Do the electrons in all atoms travel at the same speed?"
Well, in the original Bohr's model of an atom, electrons did travel at some definite speed along an orbit surrounding the nucleus of the atom. This velocity depended upon the energy of the electron, and so it was not the same, of course, for all electrons. Now, the more correct point of view of quantum mechanics is generally accepted, and according to it, an electron in an atom is represented as a cloud uniformly distributed along the Bohr's orbit.
Would you mind translating that a little, Emerson?
Well, in other words, at a given distance, an electron cannot be localized at a definite point of its orbit, and so one cannot speak of its velocity.
Now we have this inquiry. Is it safe to keep kerosene in a barrel that has been used for gasoline? If not, how can it be made safe?
It would be best to ventilate the barrel by letting it stand open and then rinse out with about a quart of kerosene. This quart of kerosene should then be thrown away. After this treatment, the barrel should be safe to use.
A friend in New York City asks if washing a man's raincoat in warm, soapy water will destroy its water resistance.
Some of the water resistance will be removed by washing, Bob. Soon there will be on the market a wax emulsion in which materials can be soaked and thereby waterproof.
And now I'd just better say thank you, Emerson Markham, and goodbye, everyone, until our next excursion in science.